In this video, we're going to discuss Maxwell's equations. Maxwell's equations describe how electric and magnetic fields behave, so understanding Maxwell will require revisiting electric and magnetic fields. The simplest way to understand fields is to think of them as a shorthand for how charges move around. That understanding is summarized in the Lorentz force equation pictured on this slide. The equation says that a particle with a charge q will experience a force in the direction of an electric field and perpendicular to a magnetic field if the charge is moving. We need to talk about the units of E field and eventually B field to cement our understanding of them. Electric field is measured in volts per meter, which suggests that it's some kind of spatial derivative of voltage. That's actually true by definition. Voltage is defined as an integral of the E field. However, the story doesn't end there. E field is only really well defined in vacuum unless we add some additional parameters to represent how E interacts with materials. P in this equation is the polarization density, which represents how charges in a material are arranged. If charges in a material are slightly misaligned, they each create a dipole moment, and the sum of those is the polarization density in this equation. Polarization density has the same units as displacement field, which is d on the left side of this equation, and both of them measure how much total charge has been moved by a field. The units of that charge displacement are coulombs per meter squared, and that's different than the volts per meter that we see in electric field. So we define epsilon, the permittivity of a material, as a constant that tells us how much charge the E field moves. Permittivity turns voltage into charge, just like a capacitor, so it has units of farads per meter. And in particular, it's 8.85 picofarads per meter in free space. There's a similar formalism for magnetic fields in materials. B is the magnetic flux density, which is measured in Tesla, and it's most closely related to forces on a charge, as we saw on the Lorentz equation on the previous page. However, we're mostly going to be using H, the magnetic field strength, in our calculations. H is handy because it relates closely to currents in a circuit, and you can see that in its units of amps per meter. Just like voltage can be defined as an integral of E field, current can be defined as an integral of H field. In this case, you have to take an integral around a closed contour of H. Finally, magnetization, M, represents magnetic fields that are built into the medium you're considering, just like polarization. And also just like polarization, magnetic fields are made up of the sum of microscopic magnetic moments. Permeability relates H and M fields to inductance the same way that permittivity relates E fields to capacitance. So it also tells us how much magnetic flux, which is the B field, is created per unit of H or M. And it has a value of 4 pi over 10 microhenries per meter in free space. You might notice that 4 pi is a little bit of a specific number that has to do with how permeability and permittivity are defined. So now that we remember what fields are, you should be perfectly prepared to remember physics class. I'd like you to pause the video and try to write down Maxwell's equations. Here they are. If you're anything like me, you didn't find these easy to remember. There's a lot of wild symbols, and the fact I was taught them in a slightly different form every time I learned them didn't help. Here's how I remember them. First, I break them into divergence, del dot equations, and curl, del cross equations. I know there's a divergence and a curl equation for both E and H. Second, I associate charge with E field and current with H field in my head. These two crutches, combined with some of the results we'll see on the next few slides, let remember that divergence for E is related to charge. Divergence for H has to be 0 because magnetic fields are loops. And curl of H is related to J, because magnetic field is related to current. The remaining time-varying terms are part of a wave equation, and I just remember to stick those with the curl equations. These are complicated equations and they have a lot of implications, but I'm going to boil it down to 3 takeaways for the purpose of this video. The first comes from this equation. It says the divergence of the E field is equal to the charge density divided by epsilon. Understanding this equation is easiest if you have a geometric picture of the divergence operator. The divergence of a vector field is a differential measure of how much it spreads out. It compares the field flux into a unit volume to the field flux out of it. And if there's extra flux leaving a differential, then the field is said to have a positive divergence. So in the example I've shown here, the same amount of field enters into the left box as leaves it, while more field enters the right box than, more field leaves the right box than enters it. That means the right field is diverging. This perspective of a divergence applied to the first Maxwell's equation says that electric field is created by positive charge and absorbed by negative charge. The other divergence equation says that H field is neither created or destroyed, which means that H field is always a loop, it turns out. The second phenomenon I want to highlight is found in this fourth Maxwell's equation. If we ignore the time derivative for a minute, we can see that the curl of H field is generated by current density. So certain current somehow creates magnetic field, or at least a field-related quantity. A geometric understanding of curl helps understand this implication. Curl can be understood as a differential measurement of how bendy a vector field is, which is a pretty informal definition. A slightly more formal one is that curl measures how much a tiny paddle wheel would spin if you dropped it into the vector field. In the left figure, our paddle wouldn't spin at all because the left and right blades are pushed the same amount. In the right figure, our field has to take a turn inside of this differential that favors pushing on the top blade of our imaginary paddle wheel, which means the paddle wheel would spin counterclockwise, implying a positive curl. So current density means that implies that there have to exist counterclockwise spinning loops of magnetic field. That fact is why we can find current by integrating around loops of H. If there's a current, there's always going to be a magnetic field spinning around it, and vice versa. The last important takeaway from Maxwell's equations is that they imply the existence of electromagnetic waves. First, we're going to imagine that we're in free space, which means there's no charge or current lying around to mess with our equations. The two curl equations look like cross-coupled differential equations. They have spatial derivatives on the left and time derivatives on the right. And last time we saw that led to waves, so we should check to see if we can make the magic happen again. We do so by first assuming we're in free space, which gets rid of any pesky charge or current lying around to confuse our equations. Then we take the curl of both sides of the del cross E equation. Then we swap the order of derivatives on the right-hand side and substitute the value of del cross H into the result. Then we simplify the left side using a vector identity that we all definitely remember. And notice that we said del dot E was 0 because we're in free space, so we can knock out one additional term. And that leaves us with a 3D wave equation. We can pick the velocity out of this equation off of the coefficient of the time term as usual, and we see that we expect a velocity of 1 over the square root of mu times epsilon. So in summary, fields are handy shorthand for forces on charges. Charge creates and destroys electric field. Current density results in a curling H field. And free space equations imply a wave that travels at a speed of 1 over the square root of mu times epsilon.